Okay, so these are the links for the slide and the YouTube video. So firstly, we will see why we need directional relaying. So let us consider here uh, two feeders. We can see this L to N and M to N, M to N connected with two sources, source 1 and source 2. So basically, if we have a fault F1, then which relay do we expect to trip? Basically, we want relay MN or relay NM to trip. And similarly, if we have a fault F2, then we want to isolate only the feeder LM. So we want only the relay LM or relay ML to trip. So we'll see one by one what will be the cases due to these two sources present. So let's say first we had a, sorry, so let's say first we had a fault here, F1. So for this F1 fault, since we are having two sources, so the fault will be fed by source 1 and source 2, right? So the current seen by this relay RMM, basically we are studying here. So we can see for fault F1, we have this dotted lines. So in the normal condition, if say the current was this waveform, and let's say at t equal to 1, we initiated a fault, then we can see the fault level has, current has increased for F1 fault, right? And similarly, let's say we have this F2 fault. So during this condition, what will be the path for the fault current? Firstly, considering the source F1, this is 1. Similarly, source 2 will also feed this fault, right? It will be this way. So if we consider, let's say, firstly we had considered, we are studying only relay MN now, and let's say for fault 1, so during normal conditions, the current was in this direction, right? I and then this I, or you can say I load. And during F1 fault, additional fault current is added in the same direction, due to which we get these solid fault current. But when F2 fault is there, we had the normal condition flowing current as this, but again it will see a large reverse flow current, right? F fault, due to which you can see you get negative current flowing here. So using this basically direction properties, we can distinguish whether the fault at this relay is behind or ahead of it. And since for F2 we don't want the relay to trip, and for F1 only it should trip. That is the ideal condition. So then let us move that why we need this adaptive protection. So firstly, as we see in the first slide, due to this multiple sources feeding the fault, we need to revisit the relay settings, and normal overcurrent relays are now not sufficient. We need to have relay with directional property. Similarly, the fault current, due to this inverted based DRs and synchronous based DRs, they are not same. Generally, synchronous based, the fault current due to this synchronous based resources, they are much greater than the inverter based resources. And in the traditional practices, the relay setting will be according to these synchronous based resources. So in case that a fault is fed by inverter based resources, the relay may not be able to sense that fault. Similarly, we may have different operating modes, maybe the grid connected or islanded mode of operation, and that will also going to affect the protection schemes. The first adaptive protection scheme that we studied in this week was based on sequence current, right? So basically this is for the primary relay, and this is
Good
for the,
evening, madam.
yes sir.
Madam, I have a doubt on this.
Huh.
Madam, why? What is the reason why source-based inverter has 5 times of fault current and inverter-based DER has 2 times of fault, 2 times of rated fault current, madam? What is the reason behind that? Why SCBR is 5 times and why inverter base is 2 times?
Okay, so if we see here, basically we need to convert this into a Thevenin's equivalent, right? So here we will have source, let's say E1, then let's say it has some internal resistance Z1, then we have the ZLM, then we have ZMN, then we have, let's say, Z2, then we have E2. And let's say for F2 fault, if we have a fault here between L and M, so that means we will have fault impedance here. This is that fault. This is IF1, this is IF2. So what will be the value of IF1? Let's say this voltage is VF, then it will be E1 minus VF divided by Z1 plus ZLM. Right, up to here we got this current flowing through here up to this, let's say this is I1. Then for IF1, again we'll be having the we can say current, it will be having two paths. So it will be basically this VF by ZF. So basically this VF we need to substitute from here. This VF will be a function of E1 and this Z, basically its internal resistance, we can say, right? Is this clear up to here? So be it be a synchronous or a inverter based resources, if we take ideally E as 1 angle 0, so the fault current that we are feeding, it will depend upon it, we can say internal resistance, this Z of the source. So if let's say I'll change this color here. So if I substitute this VF, so basically it will be I1 E1 minus I1 times this Z effective, we can say basically. So this is VF by ZF. So this is I fault. So let's say this, we can say it will be same for both of them. Then if we are having high fault current, that means this Z effective will be low, right? So from this we can deduce that if we compare the Z of synchronous based and Z of inverter based, so what will be the relation here? For synchronous based, we know that we are getting more current, right?
5 times, ma'am.
Huh.
Less than less.
No, see, we know this.
No, no, no. Inverter based is 2 times, and so synchronous based is 5 times.
Basically, we can't say this times will be uh, 2 times or 5 times. It will be accurately there because we are having other factors also, right? It is also being subtracted from something, and Z also is there. So what we can see basically, this when this I is more, means this Z must be less. So we can say I for synchronous was more, means its Z must be less, right? So is this okay?
Okay, ma'am. Thank you.
So we were here. Now let's say we have, sorry, I'll change this. So for this backup relay, we had basically this relation, and then we found the TDS using this primary and backup relay settings basically for this kind of situation where we are having multiple inverter based resources and the grid here. So maybe we can discuss for one such case. Let's say we have a fault F2 here. Then for F2 fault, what will be the primary relay which should operate? Anyone? See this feeder F2, you can say G2H. So we have R3 relay and R4, right? Because we want that only the feeder which is faulty that should be removed and the healthy part should be intact. So considering this R3 and R4 as the primary relay, can we guess the what will be their backup relays? These arrows basically representing their directional element, in which direction they will be sensing the fault. So what will be the backup relay for R3?
R2,
For R3, using R2. Okay, anyone else?
R2.
Okay. Uh, so basically, when we had a fault F2 here, we had a source feeding this way, then we had the grid feeding this way, then we had also this source, right? It was also feeding this way. Am I correct? So first we'll see.
Yes.
Okay. So we had known this R3 and R4 are the primary relays. So for R3 relay, we'll see which other relay is also seeing the fault in the same direction as this. So if we consider this source 1, which relay among R1 and R2 can see this fault? If we consider first this path, then before R3 we have R1 and R2. So among these two, one of them will be their backup relay. Among R1 and R2, this fault is in this direction, right? In forward direction. So which relay is seeing the fault in forward direction among R1 and R2?
R1.
Yeah, so it will be R1 because the current is flowing in forward direction. R2 cannot sense this fault. So for R3, we got R1 from the grid side. Then we add another source. This is DG1. So this is also feeding this fault through this path. So again for R3 we are having two options, R5 or R6, right? So again in among this R5 and R6, which relay can sense this?
R6.
Okay, we got one R6. Anyone else? Anyone else would like to answer you? See, we had the current flowing in this direction, right? So R6 can sense it. But for R5 it is in opposite direction. So R5 cannot sense it. So we can say again R6 is the backup relay. Then for R4, which one will be the backup relay for R4? Do we have any other relay before R4 in this path?
No.
We do not have any relay. That means this R4 we don't have any backup protection. Okay. Okay. Then let's say we'll consider just one more case. Let's say we had a fault F1 here. So for F1 fault, which will be the primary relays? Anyone? For this feeder EG, basically, we had a fault F1. So which will be its prime?
R1.
Any other relay, sir?
R4.
Uh, no. I'm talking about primary just now here. When we have a fault in this feeder, we expect to only isolate this feeder, right? So we have R1 here and we have R2. So the primary relays will be R1 and R2. Then next, let us see what which is the backup relay for R1. So for that, we'll see the direction of fault current. So the first path is through this, the second is through this DG1.
Ma'am, R1 doesn't have a backup support.
Okay, R1 doesn't have a backup support. Anyone else? Then we have this through this path also. Basically, since we do not have any relays before this, so R1 will have no backup support. Then what about R2,
R4 and R6.
R4 and R6? Anyone else?
R2 and R3 are the backup protection, ma'am.
R, R, sorry, can you repeat?
Sorry, R3 and R5 both are backup protection, and R2 is the primary protection.
Okay, we'll see then. Anyone else? So, okay, let us see. For this grid side, we checked there were no other relays. Then let's say for DG1, so the fault current is in this path. So you can see R6 can sense the fault current if it is in this direction, which is matching with this current situation, right? So R6 can sense it, but R5 cannot sense it because it is not matching its directional property. So first directional relay is R6. Then for this path, we had R6. Then for this DG2, again, the fault current is in this way. So here again, we can see R4 can sense it, but R3 it cannot because it is in opposite direction. So the backup relays are R4 and R6 for R2, and we do not have any backup for R1. Okay. Then we had seen this, that how the direction is estimated using the superimposed currents. So basically we computed the superimposed current as the difference between this fault current and the pre-fault current. And basically this angle was the angle of the fault current minus the angle of the pre-fault current. Similarly, for this figure we have this one. So basically we are saying, so let us consider this figure first. Um, so if you see here, the delta, or sorry, phi f1, we can see it is the angle between if1, that is this vector, and the angle between I pre. So what is this? Okay, so we have these two vectors basically, delta if1 and I1 pre. So the angle between them is phi f1. So is it positive or negative, anyone? This angle? We know here we take
It is
anti-clockwise.
negative.
We got one negative. So anti-clockwise is positive. This is our convention which we take, and clockwise is negative. right? So now anyone, so we have basically here it's like this and something like this.
Negative.
We got negative, and this was the angle here, right? So this is in anti-clockwise direction, right? No, this is in clockwise, sorry. So just a second. This is clockwise, and for IF2 we had this angle. This is in anti-clockwise. So anti-clockwise will be positive, clockwise will be negative. So so it will change when the current flow, basically if it is from the grid side upstream or in the reverse direction downstream. So we have this rule. If it's a forward fall, then the angle will be negative, and if it's a reverse fall, the angle will be positive, and it will reverse in case we have downstream. Then the next one which we saw was superimposed adaptive sequence current based protection. So here we calculated, we can say a weight. So for inverter based DERs, basically this will be, since it is a addition, we get this as greater than 1, because this will be basically 1 plus a positive quantity. So this will be, we can say, greater than 1 for the inverter based resources, and for the synchronous based DERs this will be 1 minus a positive quantity. So this will be less than 1, and this we are multiplying, we can say, here. Then in the next part we saw for the storage technologies in the grid. So basically what are the advantages of using these storage technologies, we'll see in brief. So we had discussed this also earlier. Firstly, for grid stability and reliability. So we know, since we can store the energy and use when we need it in case of contingencies, or we can say power imbalance, so we can use it at the time of need effectively. That's why it leads in stability and reliability. Then it will also help in integration of renewable energy, because since the renewables, they are intermittent in nature, we know. So whenever they are abundantly available, we can store them and then use them when there is a power deficit. They also help in peak load management. So this peak load management and time shifting we had seen. Basically by this what we are trying to do is we are trying to coordinate their charging and discharging cycles according to the need of the grid. So basically if there is a peak load going on now, then what should the battery do? Energy storage in general. If we have high load implies we have deficit of generation. So we need generation. So this is Pg and this is Pd, and we have seen that they are not equal, and in case of high load, to make it balance, so this, what should be the direction of power of this PE is? If it is injecting, it is withdrawing. Anyone, should it inject or should it withdraw, considering
Inject. It will inject, man.
it will inject? It should inject because we are having, sorry, I wrote this wrong here. High load means your load is higher here. So the mismatch should be provided by the ES. Basically here it will inject the deficit part to satisfy this load. Similarly, in the reverse case, what it will do, if we have greater generation, it will charge the excess and store it. Then for frequency, it can also provide, we have discussed various ancillary services, basically frequency, voltage, and it can also provide black start support, we had seen. And it can also help in deferral of grid infrastructure. So basically for lines or any power projects, so their need can be mitigated by the use of this storage technologies, or various Q support also, we can say capacitor bank. The need of these resources or grid infrastructure can be avoided by using this energy storage. And they'll also help in electrification of the transportation sector, basically the EVs we had. So it will also help in integrating these EVs into our grid. Because it is clear, right? Because here we are using batteries, right? In case of conventional fuel, we are using batteries to power these vehicles. Then the classification of energy storage. So depending upon which form you are storing it, from electrical to thermal or vice versa, similarly electrical to mechanical, chemical, electrochemical, you can say, we can divide them into these subcategories. So basically battery comes under this electrochemical. We had pumped hydro, flywheel coming under mechanical. Then we had natural gas and solar fuel cells as chemical energy. And for thermal, we have latent form or sensible and thermochemical energy storage under thermal energy. So how to decide what kind of battery storage system we want to deploy? So what are the factors that will help in deciding us? We'll discuss some of this point. So firstly, the capacity. So we must determine the required capacity by the battery in terms of, let's say, kilowatt hours or megawatt hours, and it will also depend upon what application you want to do, whether you want to have load shifting or backup power or grid support. So depending upon the type of application, we can decide the required capacity. Similarly, the power rating. So it is in kilowatts or megawatt, and it will indicate the maximum discharge rate of the battery, and it should be equal to the mismatch, whether it is exceed the peak power demand of the application. Secondly, battery chemistry also. We know we had lithium ion currently developing. Previously, we had lead acid batteries, which were now actually very difficult to decompose, or decompose, not we can say dispose. So again, we are now lithium ion is evolving. Then we had seen this cycle life, basically the charging discharging cycle. We had seen it in the previous, in the calendar aging and the cycle aging of the battery. So basically cycle aging will it is depending upon how you are using the battery, how frequently you are charging and discharging it. So round trip efficiency. So it is the efficiency of the battery in converting the stored energy, which it will store in the form of electrical or electrochemical, depending on the type of storage, back to the power, electrical power. So a higher efficiency will mean lower energy loss during the storage process. Then we had discussed depth of discharge, which is basically 1 minus state of charge. So then we had also discussed this response time. Now this is very crucial because when you want to have let's say frequency support, so the response time should be very fast. So depending upon the application what you want, the response time needs to be decided. Then scalability, obviously, if you want to add more modules to the existing infrastructure to mitigate or to include the growing renewable or the load. In safety, we have some safety concerns related to battery. Firstly, it being the thermal concern regarding the battery. So these need to be considered while deploying. We need to have adequate safety measures in the site. Then also environmental conditions, whether you are having extreme temperature in your region, then you should take care while cooling your battery energy storage. Then moving on, we had integration. So it should ensure the compatibility with the existing power infrastructure, basically the existing inverters and control system. So its rating should be compatible with these existing infrastructures, we can say. Then it should meet the grid codes and the compliances, we can say the standards. It should mean like we have IEEE standards, so it should follow those standards. Then we can also calculate their cost. In life cycle, we know this is a planning study we do basically. Then grid services. So as I said, the type of service that you want from the energy storage, that is very important, and according to that you can deploy the storage that is most suitable for that type of application. Then we'll see some factors that are affecting our battery performance. So firstly, obviously the battery chemistry that is going inside, so that will affect temperature. We all know it will may result in thermal runaway and damage the batteries. Then instead of charge, we know extreme charging is also not beneficial to the health of the battery. Deep discharging is also not favorable. It is not recommended. Then the rate of discharge we see. So high discharge rate may reduce the capacity of the battery and its efficiency also. Similarly, rate of charge, these are related again. Overcharging and over discharging we should avoid. Then we had also seen cell balancing in the previous lecture, passive cell balancing and active cell balancing techniques. Those should be taken care. And obviously the battery aging, we had also seen calendar aging and cycle aging. Similarly, the cell balancing, as I said, over voltage over current, how you're using it. So all these are going to affect the overall performance of the battery. The next thing we saw that we want to shift from the traditional AC grid to a DC microgrid. what are the advantages that we'll be getting. Firstly, in DC microgrid, we will be having uh, efficiency will be increased because we'll be having lower losses, and we can directly feed the DC loads and the devices, and it will be having easier integration with the DC loads. We will be no longer requiring the converters in the in between, and hence it will facilitate their integration. Then energy storage compatibility. Again, since the battery storage that we're using are basically DC type, so DC system can integrate them effortlessly. Then renewable energy. We know the solar or the wind, they are generating DC power only. So we can integrate these renewable energies also into our grid without the traditional converter techniques. They can be avoided. Then other are as we said, losses will be low, so efficiency will be higher. Then we don't have to have uh, sophisticated control systems for this. They are easier to design, operate. Then since they won't be having phase imbalance or frequency deviations, you can say they are not prone to faults and disturbances as in a AC grid. They can also be used in off-grid or remote areas, we can say, where we will be having renewables which are basically giving DC. So they can be used in remote grid applications. And since we don't have frequency here, so there will be no electromagnetic interference with the environment. Then we had seen some DC microgrid topologies, basically single bus system, multi-bus topology, and in reconfigurable, we had a ring bus, we had a zonal, and we had multi-terminal DCs. Then the sources that we are using, we saw their modeling, which we had also seen previously for solar, for wind, and for fuel cell. And the type of loads were basically three types of constant current, power, and constant impedance loads. So, but again, these DC microgrid will also be having some limitations. So they cannot be used for long transmissions. For transmission purposes, AC voltages are always preferred. Then we'll be also having voltage drop issues, basically in distribution lines where we will be having larger R by X ratios. Then the voltage regulation will be here difficult, and as you know, the currently the what we are having is AC. So we don't have adequate amount of standards to follow for the DC microgrid, and we will require again additional converters because since we are now in the AC grid, so the cost of also DC to DC converters, that will also add on to the cost. So for DC to DC converters, again we had seen boost, buck converter, boost converter, and buck boost type of converter. We'll solve a numerical upon them and we'll discuss about it. Then lastly, in the last lecture, we discussed about the AC microgrid. So this we had discussed that it can operate in grid connected or islanded mode of operation. So for grid connected mode of operation, we have two strategies, control strategies, basically feeding strategy, grid feeding and grid supporting. And for islanding mode, we need this additional one, grid forming. Along with this, we'll be having grid feeding and grid support facilities. So we'll see this one by one. So what was this grid feeding? Anyone, if you remember? Basically, They were represented as a current or voltage source. Anyone? So grid feeding, they were basically current sources with high impedance. For grid forming, we had a voltage source with lower impedance, and for grid supporting, we can have both this, or we can also have this. Basically, grid feeding mode, we were using this when we had a grid support. Grid was present. So what we were doing here, we were controlling the microgrid V and omega by using the P or Q. Similarly, for grid forming, these are special type of converters. So here, these need V and F from the grid. But about grid forming, they can work even in the absence of grid, that is in islanded mode of operation. So they will set the V and F for other inverters to follow. For other grid feeding inverters, they will set the V and F. And grid supporting, these were a special kind. So what they can do, they can operate in islanded or grid connected mode, and they can help in controlling or supporting the grid. So they can control the grid side voltage and frequency by obviously their P and Q. So lastly, then we saw the different kind of ancillary services that can be provided by these we can say inverters. Firstly, frequency support, then reduction of losses, improvement of power quality, voltage support, and congestion management. And for the islanded mode of operation, they can provide black start ancillary service and grid forming operation. So we'll see some questions on this week content. So the first question is, how are the IDMT over current release, time of operation, and time multiplier setting related? So you have four options. Is it operating time equal to TMS? Is it inversely proportional, directly proportional, or none of these? Anyone?
Inversely proportional.
Okay, we got one inversely proportional. Anyone else? You can also type in the chat box if you want. Okay, so we had seen this here, right? So Here, basically, this is the time of operation. This is the TMS. So from here you can see, so there we saw the time of operation. It was directly proportional to the TMS. So it is directly proportional. Then this was in the slides only. Using the analogy of fuel tank in a car, the SOC estimation is often called a fuel level, fuel capacity, fuel gauge, or all of the above.
Fuel level
Fuel level we got one.
or fuel gauge, we can say both are correct. Fuel gauge is correct.
Okay, fuel gauge. I will take yours as fuel gauge. Anyone else? Basically, SOC estimation. So it will tell us up to how much it is charged, and in a car that will be told by your fuel gauge. Sorry. So next, factors considered during the cell selection of battery: weight of cell, DOD depth of discharge, ambient temperature, or all of the above.
All.
Okay, we got one, all of the above.
All.
Okay, we got two. Okay, the answer will be all of the above. Can anyone say when this weight of cell will be of importance for which application?
For vehicular application, for airborne application, vehicle.
Okay, anyone else? Yeah, it is correct. For as Sir said, for EVs, so this weight of the cell or the weight of the battery in whole is very crucial. Then the operating quantity in the superimposed positive sequence method of fault direction detection is pre-fault voltage, pre-fault current, superimposed fault current, or superimposed fault voltage component.
Superimposed fault current.
Okay, option C we got one. Anyone else?
Option C, ma'am.
Okay, we got another. Yeah, basically, both of you are correct. It is superimposed fault current component. We had seen in the angle, right? Then we have a small problem. So for the boost converter, the output voltage and input voltage are 40 volts and 10 volts respectively. Then calculate the converter duty ratio.
A 0.25.
Okay, we got 1.25. Anyone else? So, can anyone help me with the formula for boost converter? It will be V. It will be V output by V input. That will be equal to 1 by 1 minus the duty ratio D. So from this, now anyone else? Anyone? So the output here is 40 by input is 10. So it will be 4. So it will be 0.75. Okay. Uh, the buck boost here we changed the converter type. Uh, Anupam sir, can you please mute yourself? Thank you. So the buck boost converters output voltage and input voltage are given as 40 and 10 respectively. So what will be the duty ratio of this converter? Basically, this is buck boost. Anyone? So its formula is V output by Vn is D times 1 minus D. So anyone here? So 40 by 10 is 4.
A is the answer.
We got 1.2.
Sorry, point 8. D is the answer. Sorry.
Okay, now let me see. We got 1.8. From here, we'll get 1 by 5 equals to D. Basically, it means 0.8. So 7 is correct. This 0.8. Then again, same, but here we have output voltage as 10 and input as 40.
Point two, ma'am.
Okay, we got 1.2.
Point 2.
Get 2 point. So 1 minus D equal to 4D. So 1 by 5 equals to D. That is 0.2. Then grid forming power converters can be represented as an ideal voltage source with low output impedance, high output impedance, zero output impedance, or none of the above.
Low output.
Okay, we got one low. Anyone else? It will be low output impedance. Then a factual question. For the operation time limit and desired CTI or coordination time interval of both the primary relay and backup relays is within which limit? 1 second and 0.3 second, 0.3 and 1 both, or 0.3 both.
D is the answer, ma'am.
D or B. Okay, we got 1B, I think. Anyone else?
Point 0.3 seconds to 0.5 seconds.
No, I think it is not in the option. You are saying 0.3 to 0.5. I think it is the range for something else. not operating time limit or CTI. Basically, we are saying operating time for both primary and backup relay. And what is this CTI, coordination time interval?
That's point 0.2 to 0.3 seconds, ma'am. Backup relay.
Huh. So this CTI is basically the time of operation between primary relay and backup relay. So basically this T operating has to be greater than CTI, right? This will be 1 second and 0.3 second. The function of microgrid ancillary services in islanding mode is black start, voltage, grid loss reduction, or all of the above.
All of
All
the above, ma'am.
Okay, beware it's islanding mode only.
and A is the answer then.
Okay. These are no doubt ancillary services, but for the grid connected mode. So the answer is black start. So any doubts or any discussion, any concept? We have ample amount of time with us. Maybe we can take one or two case studies here, I think, since we are having time. So I think we'll just take a So let's say we have your synchronous based thermal generators here, and we have a storage connected here. Then again we have, let's say, or let's say this is a, for simplicity, this is a renewable source. Let's say we have load here along with energy storage, TS2. So for let's say simplicity, we have, let's say, two intervals only, T1 and T2, or let me increase it to T3. Oh no, let's keep it as T1 and T2. Let's say for this load is having 100 megawatt, and let's say not 100 megawatt, we'll take it as varying. Let's say that line limit, like transmission line limit, that is 500 100 megawatt for this line limit. So we'll see some cases, and let's say for T1 interval, its generation is intermittent. Let's say it is generating 150 megawatt, and for T2 it is having 50 megawatt only. Similarly, we have the load profile also PD. So for T1 interval, let's say it had 50 megawatt, but in the T2 interval it wants 150 megawatt. I just swapped both of this. So now let us consider what will be the energy profile of this ES1. Okay, so let me see that positive PE. Oh, did my screen? I'll reshare just a second. Just a second, I think I am having a bad network connection. Hello, am I audible?
Yes, ma'am, you are audible, but
Okay.
your screen is not visible to us.
I got actually got disconnected from the laptop, so I
Yeah, yeah,
just
ma'am. Yes.
okay. I think now I'm reconnected. I'll present my screen. No worries. I think I will share from here. Is the screen visible now?
Yes, ma'am, it's visible now.
Okay, thank you. I think I'll have to just redraw those things. So basically what I was saying that I had basically two bus system connected with two energy storage ES2, ES1, and this was PG, and we had the maximum line limit as PMAX I can say as I told as 100 megawatt, let's say. Then we had the power profiles, basically PG for two time interval. For first time interval it was high, it was on 50, all as in megawatt. I am not writing the units now. For second it was 50, then PD.
Ma'am, your writing pad is not visible. Screen is visible, but I think you are writing something. It's not
Yes,
visible to us.
okay. I don't know. Is it visible
Yeah,
now?
now it's visible, ma'am. Thank you.
And now?
Yes, ma'am. Now
Okay,
it's visible.
okay. So for PD, I had that for first time interval. Let's say it had 50, and for second time interval, let's say it had 150. So let us consider case 1 where we did not have, let's say, no ES1 or ES2. So during that time, can anyone tell me what will be the PG curtailment? Let's say first we are telling that we don't have this ES1 or ES2.
Ma'am, for case one, power generation is greater than power demand. So the cost of electricity is more because we are making more losses. If you have to consume the electricity in a good manner, some revenue has to be collected from the customers. But in that situation, we are spending more money for making electricity.
Basically,
If it if there is any electro stash storing energy capacity, whenever power generation is greater than power demand, we can utilize for store.
so basically
But that
now,
provision is not available for case one.
true. So what will happen now? We are having 150 megawatt of generation, but the demand is only 50 megawatt. So we all know we'll be having PG equal to PD always. Let's say it is lossless now. So since we have load demand of only 50 megawatt, we have to force the generation to 50 megawatt, right? And rest, we can say if this was on 50, this much amount we have to curtail. Is it fine? That means how much we have to curtail? 100 megawatt of PG. So that means we are wasting 100 megawatt of power in the first cycle. And in the second instant, what would happen? And for first instant, PD will be 100, right? Sorry, PD will be 50 to match it. Is this clear up to now?
Ma'am, in that situation, we may go for blackout.
No, blackout won't happen. What will happen is here we'll be having spillage, means we'll have to curtail, right? We have generation 150, but since we can't have that much amount of load where we need to dissipate, because always we need to maintain PG equal to PD, right? That means
Yes, ma'am.
the extra 100 megawatt we had to curtail here.
Ma'am,
Of
this extra 100 megawatt will go for the storage.
that
That
in case one we are considering that if we did not have storage.
we have shown in the diagram that we have ES1 and ES2. So
In
both will be.
case, yes sir, in case one I am telling no ES1, no ES2.
Ma'am, power generation is only 50 megawatt, or power, but power demand needed is 150. It is
Hmm.
not possible to have it. So, 100 megawatts of electricity we are not going to provide. That's why we go for we are not going to give the electricity for 24 cross 7. We are go for some scheduling. Some part of the some area we are not going to provide the electricity if we are not going to use any storage devices.
Yeah, so now for this second part, what we'll be doing, we will be curtailing the load. So since generation is only 50 now, but the demand was 150, right? So we have to curtail the load. PD we need to curtail here 100. So if we did not have energy storage, in both the time intervals T1 and T2, we had 100 megawatt of renewable energy curtailment, and second we had 100 megawatt of load curtailment. Now let us see case 2, where now we have only ES1, let's say, and no ES2. So ES1 is present, ES2 is absent. So in this case, for the first time interval, what will happen for PG, for PD?
Size of ES1 and ES2 is how much, ma'am?
We are having, let's say this is 200 megawatt. But here in case 2, we are not considering ES2. ES2 is not there, only ES1 is there.
Yeah, during time interval T1,
Hmm,
ES1 is getting charged,
true.
and time interval T2 it will be discharged.
T2 will
100
be,
megawatts will be discharged so that we are providing electricity for 24 cross 7
okay.
with this arrangement power generation and power demand. If we had to take the case 2.
Hmm. So for case 2, for we had 150, so PG will be 150, but here PD it will be charging, right? And how much it will charge?
Yes, as 100.
100 charge.
And during T2, the same 100 megawatts will be discharged. So T1, T2, the entire period, we are providing electricity. Power generation is equal to power demand.
Okay, just a second. So PD is 50, but in the second time interval, we are having PG as 50. And if this we get 50 from here and 100 from here, that means this line has to flow 150, right? But its limit is only 100 megawatt. Are you able to get this? So even though we are having generation, we don't have enough line capacity here in the T2 interval. So are you able
50
to
is, yes, yes, 50 to be curtailed in this also.
feed to? Again, we need to curtail here. What will happen is we can only now discharge how much? PG is 50. We can discharge only 50
50.
because we have line capacity here constraint. And again, 100 megawatt of load will be shear, will be met, and again we need to curtail 50. 50 megawatt will be curtailed because of line flow limit. Then let's say case 3, ES1 is absent and ES2 is present. So during that we'll see what will happen. So what will happen here? We don't initially it is 150, right? PG is 150, but we don't have ES1, but we have ES2, right? And the load is 50. So load will be 50, and what about ES2 and PG? PG has to be here again 100 because of line limit, right? Again here 50 will be curtailed. Are you able to get it?
Yes, ma'am.
Okay, so means again 50 megawatt of energy will be curtailed. Here in the line we'll be having 100. So this 100 will be distributed. Here in the load will get 50 and this ES2 will charge, right? So ES2 will charge 50. Fine. Then in the second interval, what will happen? We have PG as 50. So PG is 50. How much is PD? PD is 150, right?
100. Yes, ma'am.
So we can only meet here 100 by discharging this 50 here. So that 50 from the generator, 50 from ES2, and total will be 100 megawatt, but still again 50 megawatt of load curtailment is there. Then lastly, we'll consider both. let's say ES1, ES2. So now okay, so what will happen? First interval PG is 150, right? And load is 50. Okay, load is 50. PG is 150, right? But now we have ES1 and ES2. So which one should we charge? Anyone? And can we again here it will not be 150, it will be
Nearby source, ma'am.
ES1. We are telling. So if we charge here, we have two options, right? Let's say we charged. How much we'll charge here then? 100, right? Is this fine here?
Yes, ma'am.
Okay. Then moving to the second case then, when we have demand of 150 now and generation is 50. So what we'll do now? Generation is 50. We have demand 150. How much demand can we meet? Again, we can meet only 100 megawatt, right? Because line limit is there. But we can charge the excess here. How much we will charge here? Here now it is 50. It is 150. So how much can we discharge this ES1? 50, right? Because line flow limit is there. Am I correct? So again, it will be here 50 megawatt of curtailment.
Then what is the need of ES2 in that situation, ma'am?
That we will see that instead of ES1, if we had charge ES2, then what we will have. Basically, I want to convey something and I'll convey that. So here then
Okay,
again,
ma'am.
we discharge 50 megawatt, right? And ES2 did not have any role here. Let's say in the T1 interval, instead of using ES1, we had used ES2. So in that case, what would have happened? We had 150 megawatt of generation, 50 megawatt. So in that case, ES2 will be charged to 50, but we need to curtail the generation here, 100. 50 is curtail. right? 50 we need to curtail. So basically 100 megawatt of went here, 50 went to load, and 50 went to ES2. And what about the second time interval? We had PG 50 and we have 50 from the, so here it will remain as 50. This ES2 will discharge 50, right? And the load demand when mate will be again 100. So again 50 curtailment here. So I know it was actually a bit confusing, but can anyone like infer like which was more suitable to use ES1 or ES2? Let us say for ES2, what we had to curtail in T1, we had to curtail 50 PG in T1, and in T2, we had to curtail 50 PD. But what about ES1? When we had ES1, how much we curtailed? We curtailed only 50 PD. Is this clear? So among this, which one would be more beneficial to use? Anyone? We had here more amount of curtailment, right? So using this ES1 was better. So basically what I wanted to convey that when in a power system where we have this time varying generation and demand with multiple energy storage, so the decision to charge and discharge, that is also crucial, and that is done in day ahead during the planning work. We formulate this like as I showed you for two interval, for all 24 interval such type of planning is done with the help of binary variables basically, and then we decide that how which energy storage we need to charge, which we need to discharge to have minimum amount of loss of load. So was it clear, or it was very, I know it was a bit haphazard, but I hope I was able to convey what I was trying to say. Firstly, we saw that with the energy storage we are able to save something. Then lastly, when we had both, we can say that the decision to take which one to charge and discharge, that will also play a crucial role. So that's why we have a day ahead planning of how the scheduling is going to be there for the next day. Hello. So was this clear to everyone?
Yes.
Yes, ma'am.
Okay, thank you. So actually I wanted to I also saw a case basically. There is one there is one concept called virtual power lines. So So this virtual power lines means basically we have a combination of energy storage with us, and we then charge and discharge them in a coordinated way so as to defer the grid investment. So what I meant to say is this virtual power lines means we had again one constraint here, that due to this line flow capacitor limit, even though we had energy storage, we had some spillage of, let's say, renewable or load curtailment. So virtual power lines means that we will have enough storage here, so that even if it is 150 megawatt of load, it means that always here we needed another line to supply this 150 megawatt here. But let's say in cases where it does not want any load, in those cases we can charge it and discharge it during the peak demand, so that we don't need any extra lines to support this power. So is this clear or was it confusing?
Yes, ma'am. Clear. Thank you.
Okay, so this is one of the upcoming like keywords, which is virtual power lines. So in that, this signifies that using this energy storage, we can also defer the investment in grid infrastructure for the power lines. And here also we saw how it helped in renewable integration and peak demand. It can meet. Okay. Any other queries? Okay, then I think we will close the session. Thank you everyone for joining, and we'll meet in the next week.
Thank you, ma'am.
Thank you, sir.
Thank you.
Thank you, sir.